Every night, when you step outside and look up, you're not looking into space, you're looking into history. Each twinkle of starlight that reaches your eyes is ancient. Some of it began its journey before humans even existed. That light left its home, crossed countless light years, dodged dust clouds, passed by galaxies, and finally ended up on your retina. It's like getting a message in a bottle tossed into a cosmic ocean billions of years ago. The universe, as it turns out, is a terrible pen pal. It takes forever to reply. But the real twist? Those stars and galaxies aren't just far away. They're moving away. The space between us and them is stretching, and that stretching changes the very color of the light we see. It's as if the universe has been playing a slow-motion video since the beginning of time. And we're only now noticing how much the footage has lagged. This strange effect is called redshift, and it's one of the most quietly profound discoveries in science. It tells us that the universe isn't static. It's alive, dynamic, and constantly expanding, dragging time along with it. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes, it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Here's a fun thought experiment. Imagine you are at a concert, and the singer belts out a note. If the singer suddenly starts walking backward while singing, the note's pitch seems to drop. It sounds lower. That's a Doppler effect. Now, replace the singer with a galaxy, the sound with light, and the concert hall with the entire universe. As the galaxy moves away, its light shifts toward the red end of the spectrum. That's redshift. It's the universe's way of saying, "Hey, I'm still moving, don't get too close." But this is more than just a quirky color change. Redshift is a cosmic fingerprint, proof that the universe is expanding. Every photon that leaves a distant galaxy gets stretched as space itself stretches. If the universe were a loaf of bread, galaxies would be raisins baked into the dough. As the dough rises, the raisins move apart. Not because they're walking away from each other, but because the dough between them is expanding. The light traveling between those raisins, between those galaxies, gets pulled too, its wavelength stretching longer and longer. By the time it reaches us, it's redder, older, and slower. That's what makes redshift so special. It's not just a visual phenomenon, it's a time machine. When we observe galaxies billions of light years away, we're looking at them as they were billions of years ago. The farther away they are, the older the light. So, when astronomers say they've seen the early universe, they don't mean they took a quick peek behind the curtain. They mean they've captured light that's been traveling toward us since the cosmos was a newborn. And here's where things start getting beautifully weird. Because space is expanding. That light's journey isn't as simple as a straight line from there to here. As the photon travels, the space it moves through keeps stretching, like a treadmill that keeps extending under its feet. The poor photon never gets a break. It's constantly losing energy as it moves through expanding space. This is why light from distant galaxies appears dimmer and redder than it was when it started. It's tired, but in a cosmic sense. It's tempting to think this means the universe itself is slowing down, but that's not quite right. What's really happening is that time, as we experience it, doesn't behave the same way across vast cosmic distances. The universe isn't one synchronized clock ticking evenly everywhere. It's a field of clocks, each one slightly out of step with the others, depending on how far they are and how fast space is stretching between them. When we look at distant galaxies, their clocks appear to tick slower, their explosions unfold in slow motion, their light pulses drag. From our perspective, time is stretching out there, but for them, it's perfectly normal. Think about that for a second. The deeper we look into space, the more we're peering into slowed-down moments of history. A galaxy, 1 billion light-years away, is living life in the slow lane, from our point of view, while nearby galaxies keep time with us. It's as if the cosmos itself is a massive theater where each row is playing the movie at a slightly different speed. So, is time really slowing down? Kind of, but only from where we stand. Time in the distant universe flows just fine for the galaxies living there. It's only when their light arrives here, stretched and redshifted, that it tells us how much the universe has expanded since it left. The more redshifted the light, the longer the journey, and the older the story it tells. That means every time you look at the night sky, you're not just looking into space. You're looking into a cosmic timeline that starts at your eyes and stretches all the way back to the beginning of everything. The stars you see tonight may no longer even exist. Their light is their final postcard, a message that says, "I was here once," sent across billions of years of expanding time. And that's the haunting beauty of Redshift. It's not just about color or motion or distance. It's about time itself being pulled apart by the expanding fabric of the universe. The cosmos isn't just getting bigger. It's rewriting its own sense of rhythm. We live in a universe that's constantly moving, constantly stretching, and constantly reminding us that even time isn't immune to change. So next time you stare up at the stars, remember, you're not looking at the universe as it is. You're watching its greatest flashback, playing in glorious slow motion, one stretched out wavelength at a time. To understand redshift, you first have to understand light not as a beam or a ray, but as a rhythm, a wave that vibrates through space with a specific tempo. The faster it vibrates, the bluer the light. The slower it vibrates, the redder it becomes. Every color in the rainbow is really just light moving to a different beat. When scientists say light is redshifted, they mean that its once rapid tempo has slowed down. The waves have stretched out, and its color has shifted toward the red end of the spectrum. It's as if the universe took a high-pitched note and dragged it into a low cosmic hum. Now, imagine this. A photon, a particle of light, sets off from a distant galaxy billions of years ago. At that moment, it's a spry, energetic traveler, bouncing along through space with a tight, short wavelength. But as it journeys across the cosmos, the very fabric of space stretches under its feet. It's like running on a treadmill that keeps expanding in all directions. The photon doesn't slow down. Light always moves at the same speed, but its wavelength does. It gets stretched, elongated, like taffy pulled by invisible hands. By the time that photon finally reaches our telescopes, it's been stretched so much that it looks redder than when it began. That's redshift in action, a record of the universe's expansion imprinted directly onto the color of light. But redshift isn't just a single thing. It comes in flavors. Astronomers recognize three main types, each with its own cosmic personality. The first is Doppler redshift, which happens when an object moves away from you. This is the same effect you hear when an ambulance passes by. The siren's pitch drops as it speeds away. The second is gravitational redshift, predicted by Einstein's theory of general relativity. This one happens when light climbs out of a strong gravitational field, like escaping from a black hole's neighborhood. The gravity stretches the light's wavelength as it struggles upward, making it redder. The third type, and the one that concerns our expanding universe, is cosmological redshift, which happens not because galaxies are flying through space, but because space itself is expanding and carrying the light with it. Here's the key difference. In a Doppler shift, motion through space causes the wavelength change. In a cosmological redshift, motion of space itself does the stretching. It's not that galaxies are speeding away from each other through a pre-existing void. The void itself is expanding. Imagine dots drawn on a balloon's surface. As you blow up the balloon, the dots move apart, not because they're crawling away from each other, but because the surface between them is growing. Light traveling along that surface gets stretched with it, and by the time it reaches another dot, say Earth, it's longer and redder. This stretching doesn't just change the light's color, it drains its energy. Light with a longer wavelength carries less energy, so redshifted light arrives tired. Not tired in a human sense, but cosmically fatigued. It left its home galaxy brimming with youthful energy, but by the time it reaches us, it's aged billions of years and lost a bit of its vigor. That's why redshifted galaxies appear dimmer and fainter the farther away they are. The light hasn't just traveled far, it's been subtly robbed of energy by the universe's constant expansion. Redshift is also one of the most powerful tools astronomers have ever discovered. It's their ruler, their clock, and their time machine rolled into one. By measuring how much a galaxy's light is redshifted, scientists can calculate how far away it is and how fast the universe has expanded since that light left. The bigger the redshift, the more the universe has stretched, and the farther back in time we're looking. This is how we know that distant galaxies aren't just far, they're ancient snapshots from an earlier cosmic era. Every redshift measurement adds another line to the universe's diary. If you could see redshift in real time, it would be like watching a cosmic slow dance. The stars wouldn't seem to move much, but their light would subtly shift as the years passed. Unfortunately, the universe plays out at a pace so glacial that you'd need millions of years to notice the change. Our telescopes, however, can cheat time. They collect light from billions of years ago, giving us a timeline compressed into a single view. Looking through a telescope is like scrolling through the universe's photo album, with redshift acting as the caption that tells you how old each picture is. And here's something fascinating. Not everything in the sky is redshifted. Some nearby galaxies, like the Andromeda galaxy, are actually blue-shifted. Their light is compressed instead of stretched. That's because Andromeda is on a collision course with the Milky Way. Don't panic, though. It won't happen for another 4 billion years. When it does, the two galaxies will merge in a brilliant display of cosmic choreography, their light shifting from red to blue as they rush toward one another. It's the opposite of redshift, a reminder that not everything in the universe is drifting apart. Some things are still falling together, but on the grandest scales, redshift wins. It's the evidence that the universe is expanding, that everything is moving away from everything else. When scientists first discovered this, it shattered the old idea of a static cosmos. The universe wasn't sitting still. It was stretching, growing, evolving. Redshift became the heartbeat of cosmic history, the faint whisper of expansion echoing through every photon that reaches our eyes. In the end, redshift is more than a color change. It's a story written in light. Every beam from a distant galaxy carries within it the tale of the universe's growth, its stretching, its relentless passage through time. When astronomers decode that story, they're not just reading colors, they're listening to the rhythm of an expanding cosmos. Light, the most constant traveler in existence, is also the most honest historian. It doesn't lie about where it's been. It simply arrives, redder, older, and a little more stretched than before, bearing witness to the universe's endless motion. Before Edwin Hubble pointed his telescope toward the heavens in the 1920s, scientists believed the universe was eternal and unchanging. A kind of cosmic museum where galaxies sat neatly in place, gathering dust but not moving. Space was considered a grand, silent stage, and everything in it was part of a still life. Hubble's observations changed that narrative forever. When he studied the light from distant galaxies, he discovered something startling. Their light was redshifted, stretched toward the red end of the spectrum. The farther away a galaxy was, the more its light was stretched. That could only mean one thing. Those galaxies weren't just sitting there. They were moving away from us. And the farther away they were, the faster they were retreating. At first, this seemed like the universe had a personal grudge against us. Everything was fleeing Earth at top speed. But the truth turned out to be far more elegant. It wasn't that galaxies were moving through space. It was that the space between them was expanding. The galaxies were more like markers on an inflating balloon. As the balloon expands, the markers all move away from one another, even though none of them are actually moving across the balloon's surface. This realization was like discovering that reality itself has been stretching under our feet all along. Hubble's discovery gave the universe motion. It meant that if everything is moving apart now, then long ago, everything must have been closer together. So close, in fact, that all of space, time, and matter once fit into an unimaginably dense point. That idea became the foundation for what we now call the Big Bang. Not an explosion in space, but an explosion of space. The universe didn't expand into empty space. Space itself expanded, carrying galaxies along for the ride. It's a subtle distinction, but an important one. If you could somehow rewind time, you wouldn't see galaxies crashing into a single point in space. You'd see all of space itself shrinking, the cosmic fabric folding back in on itself until the distances between everything collapsed to nothing. Now, expansion might sound like something you could notice. You might imagine your coffee mug getting farther from your spoon, or your car expanding slightly while you drive. But don't worry, your kitchen isn't inflating, and your morning espresso isn't about to escape orbit. On small scales, gravity, electromagnetism, and molecular forces hold things tightly together. The universe's expansion only dominates on the grandest scales, between galaxies and clusters of galaxies where gravity grows weak and space can do its stretching act unhindered. So what exactly is expanding? Space-time itself. You can think of it as the invisible stage on which the universe performs. It's not made of any substance, yet it has measurable properties. It can curve, bend, and stretch. When we say the universe is expanding, we mean that the distances defined by that stage are increasing. Imagine laying down a grid across the cosmos. Over time, each square of the grid grows larger, even though the grid itself still covers everything. The galaxies, pinned to the grid, simply move apart as space grows between them. This realization led to one of the most elegant mathematical descriptions in science, the metric expansion of space, predicted by Einstein's general theory of relativity. Einstein's equations showed that space-time isn't a fixed backdrop. It's dynamic, malleable, responsive to energy and matter. For a while, Einstein himself resisted this idea. He even introduced what he called the cosmological constant to keep the universe stable and prevent it from collapsing or expanding. Later, when Hubble's observations proved the universe was expanding, Einstein reportedly called that constant his greatest blunder. Ironically, that same concept, reinterpreted as dark energy, would make a triumphant comeback decades later as the force driving the universe's accelerated expansion. To picture how this works, imagine a loaf of raisin bread baking in the oven. The raisins represent galaxies, and the dough is space. As the bread rises, the raisins all move farther apart. There's no center raisin doing the pushing. The dough is expanding uniformly everywhere. No matter which raisin you're sitting on, you'll see all the others moving away from you. That's a remarkable thing about cosmic expansion. It looks the same from every vantage point. There is no cosmic center, no privileged position in the universe. From every galaxy's perspective, everything else is retreating. But the expansion isn't uniform forever. Early in the universe's life, gravity fought fiercely against it. Galaxies formed because matter clumped together faster than space could tear it apart. Over billions of years, the balance between gravity pulling things together and expansion pushing them apart has shifted. For a long time, gravity won on small scales, forming stars, galaxies, and clusters. But on the largest scales, expansion began to dominate. And now, due to a mysterious force we call dark energy, the expansion is actually speeding up. It's almost poetic. The universe started as a furious burst of energy, slowed down under its own gravity, then began to accelerate again, as if deciding that eternity wasn't waiting around. Expansion means that every second, galaxies are growing farther apart, the light between them stretching thinner and the cosmic distances growing vaster. In a few trillion years, galaxies beyond our local group will drift so far away that their light will never reach us again. Future astronomers, if there are any, may look up and see only the faint glow of our own galaxy group, unaware that an entire universe once sparkled beyond it. The expanding universe tells us something profound about existence itself, that change isn't an exception, it's the rule. Everything from atoms to galaxies participates in this grand stretching of reality. Expansion is not a distant concept. It's the heartbeat of the cosmos, the quiet rhythm that has carried us from a dense, blazing origin to the vast, intricate universe we inhabit today. So the next time you think about the universe, don't picture it as static, cold, or still. Picture it as a great cosmic balloon, still inflating, still evolving, still carrying galaxies like tiny jewels on an ever-growing tapestry. The universe is, quite literally, in motion, and we're all along for the ride, sitting on one of its raisins, wondering just how big this loaf can get. Time, as far as we can tell, doesn't like being rushed. It's one of the most stubborn and flexible features of the universe, simultaneously absolute and relative, depending on who you ask and how fast they're moving. When we talk about light stretching as the universe expands, we're not just talking about the lengthening of wavelengths. We're talking about a deep, almost poetic connection between light and time itself. They move together, stretch together, and tell us something profound. In a universe that's constantly expanding, time is not the same everywhere. Let's start with something simple. Light is more than illumination. It's a cosmic messenger. Every photon that reaches your eyes or your telescope carries not just energy, but a record of the time it's traveled through. When that light comes from a distant galaxy, it's been on the road for billions of years. But because space has been stretching during its journey, the light's wavelength has stretched too. That stretch is measurable, and it's the same kind of stretch that affects how we perceive time. In an expanding universe, the two are inseparable. Here's the strange part. If we could watch a distant galaxy explode in a supernova, a star collapsing into itself and blasting out light, we'd see the explosion unfold in slow motion. From the galaxy's own point of view, the entire event might take a few seconds. But by the time the light reaches us, that same sequence could appear to last twice as long. The universe's expansion has stretched not just the color of the light, but the pacing of the event itself. In essence, the farther away something is, the slower it seems to move through time. This phenomenon is known as cosmic time dilation, and it's one of the universe's most subtle but spectacular tricks. The idea that time flows differently depending on where and when you are might sound like a paradox, but it's actually a direct consequence of Einstein's theory of relativity. According to relativity, time and space are woven together into one fabric, space-time, and that fabric can stretch, warp, or twist depending on the conditions. When light travels through an expanding universe, the very metric of space-time it moves through is changing. Every second that passes in a distant galaxy might stretch into 2, 3, or even 10 seconds by the time it's observed from Earth. It's not that the galaxy itself is moving slower. Locally, in its own cosmic neighborhood, everything feels normal. Its stars burn, its planets orbit, and its clocks tick just as ours do. But from our perspective, far across billions of light years and an ever-growing expanse of stretched space, those same motions appear to slow. It's like listening to a record player that gradually drifts out of tempo the farther away you stand. The song itself hasn't changed. It's the distance and the medium that distort it. What's remarkable is that astronomers can actually see this effect. When they observe distant supernovae, massive stars that explode with incredible brightness, they can measure how much slower the explosions appear compared to similar ones nearby. These explosions serve as natural cosmic stopwatches. Their light curves, how bright they are over time, reveal the stretching of time itself. Observations show that the more distant a supernova is, the more its timing appears to slow down, exactly matching what relativity predicts. The universe is literally showing us its slow-motion replay. You could think of this as the universe's way of syncing its clock across space. Time doesn't tick in perfect unison everywhere. It's stretched and skewed by expansion. For us on Earth, seconds and minutes feel consistent, but across the cosmos, the same second could mean something entirely different. Imagine two cosmic observers, one on Earth and one in a galaxy 10 billion light-years away. If both flash a light once every second according to their local clocks, the observer on Earth would see the distant galaxy's flashes arriving more and more slowly as the universe expands. It's a gentle reminder that time, though deeply personal, is not universal. Even more fascinating is that this stretching of time means we're constantly peering into slower eras of the universe. The farther we look, the earlier and slower the cosmos appears. The first galaxies we can observe, those formed just a few 100 million years after the Big Bang, seem to move in a languid ballet. Their light pulses crawl, their motions drag, and their flickers stretch out over ages. The young universe was fast and furious, but from here, its ancient light plays back like a cosmic movie in half-speed. This isn't just a visual quirk, it's a clue to how reality works. Space-time doesn't have a single tempo. It flexes with expansion, and time itself is elastic. You can see the evidence in how the light from distant quasars flickers more slowly than light from nearby ones, or how the ticking of distant cosmic clocks stretches across billions of years. Light and time, bound together, reveal the universe's evolving rhythm. What's truly humbling is that this cosmic slowdown isn't something you can feel. Time feels constant to us, because we live inside our own patch of the universe where everything is expanding together. Your heartbeat, your aging, your morning alarm, they all move in sync with your local piece of space-time. You're expanding right along with the universe, so you never notice it. It's only when you compare clocks across vast cosmic distances that you realize time itself has a sense of humor. Think of the cosmos as an orchestra. Each galaxy is an instrument, playing its tune in perfect time from its own seat. But because the concert hall, the universe, is expanding, the notes from distant instruments take longer to reach us. Their rhythms sound slower, deeper, stretched. We're hearing the universe's symphony not as it's being played, but as it echoes through time, warped by the very fabric it travels through. So, when we look up at the sky and see distant galaxies flickering faintly, what we're really seeing are moments of ancient time slowed down by cosmic expansion. Those galaxies are living in a tempo we'll never experience directly. Their seconds last longer, their movements unfold more gently. Light and time stretch together, inseparable dance partners in the grand waltz of the universe. It's not just a poetic metaphor, it's physics written across the stars. And it means that when we gaze deep into the night, we're not just seeing light from far away. We're seeing time itself, stretched thin across the expanding fabric of the cosmos. whispering the story of a universe that refuses to stand still. Every science fiction fan knows the rule. Nothing moves faster than light. It's the cosmic speed limit, the ultimate "you shall not pass" written into the fabric of physics. Einstein's theory of relativity put it there, declaring that the speed of light, roughly 300,000 kilometers per second, is the fastest anything can go through space. But what Einstein didn't forbid was the stretching of space itself. That loophole, it turns out, is the key to understanding how the universe plays by the rules while appearing to break them in spectacular fashion. Let's start with the basics. When we say nothing can move faster than light, we mean nothing can travel through space faster than light. If you were in a spaceship and tried to outrun a photon, the laws of physics would politely laugh in your face. The faster you go, the more energy it takes to accelerate, and the closer you get to light speed, the more your mass effectively increases. To actually reach light speed would take infinite energy, and infinite energy is a luxury even the universe can't afford. But here's the twist. Space itself doesn't move through space. It doesn't have to obey the same rules as objects within it. Picture the universe as a giant piece of stretchy fabric. The galaxies are like coins glued to it. When you pull the fabric, the coins move apart, not because they're sliding along the surface, but because the surface itself is expanding beneath them. In this picture, no coin ever breaks the speed limit, because none of them are moving through the fabric at all. It's the fabric that's stretching, carrying them along. This distinction between motion through space and motion of space is subtle, but it's everything. When astronomers say distant galaxies are receding faster than the speed of light, they don't mean those galaxies are revving cosmic engines and zooming through the void. They mean that the space separating us from those galaxies is expanding so quickly that the total rate at which they're receding exceeds light speed. It's not a speed in the traditional sense, it's a stretching rate. No physics laws are broken, no tickets are issued by the cosmic police. Imagine an ant crawling along a balloon. To the ant, the surface of the balloon is its entire universe. If the balloon starts inflating, the ant sees points on the surface moving apart faster and faster. But the ant isn't running faster. The balloon's geometry is changing beneath its feet. Now, scale that up by a few dozen orders of magnitude, and you've got our universe. Space is the balloon, galaxies are the ants, and the air pump is, well, whatever mysterious mechanism drives cosmic expansion. Einstein's relativity doesn't collapse under this idea. It actually predicted it. His equations describe how space-time behaves when it contains energy, and the universe is absolutely packed with energy. When Edwin Hubble discovered that galaxies were redshifted, meaning their light was stretched, it implied that the distances between them were increasing. The geometry of the cosmos itself was expanding, and as that expansion continued, it created a bizarre but perfectly legal situation where galaxies beyond a certain distance recede faster than light can ever travel to reach us. This leads to one of the strangest concepts in cosmology: the cosmic horizon. Beyond a certain distance, roughly 46 billion light-years away, galaxies are moving away from us so quickly that their light will never reach Earth, no matter how long we wait. Not because the light isn't moving fast enough, but because the space it's traveling through keeps expanding faster than the light can cover it. The photon keeps running, but the finish line keeps stretching away. The result? Those galaxies fade beyond view, slipping over the cosmic horizon forever. Now, before you start worrying that the universe is breaking apart like some kind of cosmic rubber band, relax. Locally, everything is fine. Gravity and other forces keep galaxies, solar systems, and atoms comfortably bound. The expansion of space only dominates over immense distances, where gravity's grip weakens. On your morning commute, space isn't expanding under your car tires. The fabric of the universe stretches most noticeably between galaxies, not between your shoes and the sidewalk. Still, it's a mind-bending concept. Light, our fastest traveler, the speed champion of the cosmos, can actually lose a race to geometry. If you sent a beam of light toward a galaxy already beyond that horizon, it would never arrive. Not because the light failed, but because the universe cheated by changing the track mid-race, and the finish line doesn't just move, it accelerates away. And yet, relativity remains perfectly happy with this. The rule that nothing moves faster than light applies to local motion, not to the expansion of space itself. If you and I were sitting on neighboring galaxies, separated by a small enough distance, neither of us could move away from the other faster than light without violating physics. But as that distance grows, the expansion between us adds up. Each tiny stretch of space expands by a small fraction, and those fractions multiply across billions of light years until the cumulative effect surpasses light speed. It's almost poetic. The farther away something is, the faster it seems to flee, not because it is running, but because the universe between us keeps growing. This is what Hubble's law tells us. The recession speed of a galaxy increases with distance. The universe is like an elastic sheet being pulled from all directions at once. From any galaxy's point of view, everything else appears to be moving away, but there's no center of expansion. Every point is the center, and no point is privileged. Now, if you're wondering whether this means the universe has edges, some cosmic wall beyond which there's nothing, the answer is no. Expansion doesn't require edges. It's not like a bubble inflating into a bigger space. It's space itself that's inflating. The universe isn't expanding into something, it's simply getting larger in its own dimensions. If you could travel to the edge of the observable universe, you'd find that space looks the same there as it does here. The horizon isn't a wall. It's a limit to what light has had time to reach us since the beginning. So yes, the universe plays fast and loose with its own rules, but never unfairly. Space can expand faster than light. Galaxies can recede beyond reach, and the cosmic horizon can keep slipping away. But Einstein's physics still stands strong, quietly nodding in approval from the sidelines. The universe isn't breaking the speed limit. It's redefining the highway altogether. In the end, the speed of light remains the ultimate yardstick, not for the motion of space, but for motion within it. Light is the cosmic messenger, forever chasing an ever-stretching horizon. It never catches up, but it never gives up either. And in that eternal chase lies the rhythm of the expanding universe. Geometry in motion, infinity in progress, and the gentle hum of space itself, stretching toward forever. If you've ever stood on the side of a road and listened to an ambulance race by, you've already experienced one of the universe's simplest and sneakiest illusions, the Doppler effect. The siren's pitch rises as it approaches you and drops as it speeds away. It's not that the ambulance changes its tune mid-drive, it's that the motion between you and the source changes how you perceive the sound waves. As the vehicle moves toward you, the sound waves bunch up. As it moves away, they stretch out. Closer waves mean higher pitch. Stretched waves mean lower pitch. That's Doppler 101. Now, replace the ambulance with a star or galaxy and the sound waves with light waves, and you get something similar. Light waves, too, can bunch up or stretch depending on the motion of their source. When an object moves toward us, its light waves compress, shifting toward the blue end of the spectrum, blue shift. When it moves away, the waves stretch toward the red end, redshift. Astronomers call this the Doppler redshift, and it's been one of the most useful tools in measuring motion in space. For nearby stars, galaxies, or even the rotation of planets, this effect gives us a direct way to measure how fast something is coming or going. But the universe, as usual, takes that simple idea and adds a twist that could give Einstein a headache. There's another kind of redshift, cosmic redshift, and while it looks similar, it doesn't come from motion through space at all. It comes from space itself stretching. The difference between these two kinds of redshift is subtle but profound. Doppler redshift is about things moving through space. Cosmic redshift is about space expanding between things. To understand the difference, imagine you're floating in the middle of a calm lake. You toss a stone, and ripples spread out in perfect circles. Those ripples are like light waves traveling through space. Now, suppose the water itself starts expanding while the ripples move. The waves don't just spread out because they're moving, they're also being stretched because the lake is literally getting bigger under them. That's what happens to light traveling through expanding space. Even if the galaxy that emitted the light isn't moving in the usual sense, the space between you and it is growing, stretching the light waves as they go. This distinction was one of the key insights that transformed our understanding of the cosmos. Before Edwin Hubble's discoveries, scientists thought redshift was purely a Doppler effect, a sign that galaxies were physically flying away through a static universe. But Hubble's measurements showed that the redshift wasn't consistent with ordinary motion. The farther away a galaxy was, the greater its redshift, and the relationship was perfectly proportional to distance. That pattern couldn't be explained by simple movement through space. It required a deeper cause. Space itself was expanding. Cosmic redshift is like a built-in fingerprint of the universe's expansion. It's not a Doppler shift from motion, but a record of how much the universe has stretched since the light was emitted. When astronomers measure the redshift of a distant galaxy, they're not just measuring velocity, they're measuring history. They can tell how much the universe has grown since that light left. The more the light is stretched, the older the story it tells. It helps to picture both effects side by side. If you had a galaxy that was physically moving away through space, that's the Doppler effect. Its light waves stretch because of motion. But if you had two galaxies sitting still on the fabric of expanding space, they'd still drift apart because the fabric itself is stretching. Their light waves would lengthen not because of speed, but because their entire playground is growing beneath them. The light doesn't notice a speed. It just rides the wave of expanding geometry. Here's a fun way to visualize it. Imagine two dots drawn on a rubber band. You mark a tiny wave between them with a pen. One little squiggle. Now start stretching the band. The squiggle stretches too. It gets longer and longer. You didn't move the dots along the rubber band. They stayed put. But the space between them grew. That's what happens to light traveling through an expanding universe. The rubber band is space-time, and as it stretches, it drags the light waves along for the ride, making them longer and redder. The difference between Doppler and cosmic redshift also changes how we interpret the universe's shape and fate. The Doppler effect deals with relative velocity. It's about how things move in relation to one another. But cosmic redshift deals with the evolution of space-time itself. It's about how the universe's geometry changes over time. Measuring cosmic redshift isn't just about tracking galaxies, it's about taking the universe's pulse. Each measurement gives us a snapshot of how fast the cosmos was expanding at a given moment in its history. When scientists mapped thousands of galaxies and their redshifts, they effectively created a time-lapse video of the universe growing from its fiery beginnings to the vast, stretched-out expanse we see today. And here's where it gets poetic. The light we receive from distant galaxies has been stretched by both effects at once. For nearby galaxies, those relatively close in cosmic terms, most of the redshift comes from Doppler motion, because they're moving through space more than they're carried by its expansion. But for faraway galaxies, the cosmic redshift dominates. Their light has traveled for billions of years, through expanding space that has stretched it beyond recognition. The difference is like comparing a car driving away on a road to a car sitting still on a road that's being rolled out beneath it. If you ever want to feel humbled by physics, consider this. Light from some galaxies has been so redshifted that it's no longer visible to the human eye. It's stretched beyond the visible spectrum into infrared or even microwave wavelengths. Telescopes like the James Webb Space Telescope are designed specifically to catch that ancient, stretched-out light. Light that started its journey when galaxies were just forming, when space was denser, younger, and bluer. That light has fought cosmic expansion for billions of years to reach us, each photon carrying the scars of its long, stretched voyage. So, the next time you hear an ambulance wail and fade into the distance, think of it as a tiny, earthbound echo of something grander. The same principle that changes the pitch of a siren helps us understand how the universe itself evolves. The Doppler effect tells us about motion. The cosmic redshift tells us about existence. The siren fades because the ambulance is driving away. But the galaxies, their siren never changes pitch. It's the road beneath them, the fabric of the cosmos, that keeps getting longer, carrying their light farther and farther into the infinite, humming expansion of everything. When Edwin Hubble peered through the 100-inch Hooker telescope at Mount Wilson in the late 1920s, he didn't expect to stumble upon one of the most profound truths about existence. The universe itself was on the move. At the time, astronomy was in a state of comfortable ignorance. Many scientists thought the Milky Way was the entire universe, a lonely island of stars in an endless, empty void. But as telescopes improved, it became clear that those faint, fuzzy patches in the night sky, previously dismissed as nebulae, were actually entire galaxies, each containing billions of stars. The cosmos was suddenly much larger than anyone had imagined. Then came Hubble's revelation. By studying the light from these galaxies, Hubble noticed something peculiar. Their light was redshifted, meaning it was stretched toward longer wavelengths. More importantly, the amount of redshift wasn't random. It followed a pattern. The farther away a galaxy was, the more redshifted its light appeared, and therefore, the faster it seemed to be moving away from us. Hubble plotted these distances and velocities on a graph, expecting a chaotic mess. Instead, he found a beautiful straight line. The slope of that line became known as the Hubble constant, and the relationship it revealed became Hubble's law. Velocity equals distance times the Hubble constant. In simpler terms, the farther a galaxy is, the faster it's receding. It was the first evidence that the universe isn't static. It's expanding. Space itself is growing, and galaxies are carried along like dots on an inflating balloon. But the most mind-bending part of Hubble's discovery wasn't just that galaxies are moving away, it's that every galaxy sees the same thing. From any vantage point in the universe, every observer would see other galaxies receding in every direction. There is no cosmic center, no privileged position from which the expansion originates. It's not an explosion with debris flying outward, it's an expansion of the fabric of space itself. The universe doesn't have an edge. It's expanding everywhere at once. This concept shatters the idea of a universal here. Imagine you're standing on the surface of a balloon, covered in dots that represent galaxies. As the balloon inflates, every dot sees all the others moving away, and the farther they are, the faster they recede. There's no central dot on the surface. It's all relative. If you could somehow flatten yourself onto the balloon and live within its two-dimensional surface, you wouldn't be able to point to a center because the expansion happens uniformly. That's how our three-dimensional universe behaves. From any galaxy's perspective, the universe looks like it's expanding away from it. This has an emotional poetry to it, too. We often talk about the loneliness of space, but this takes it to a cosmic level. Every galaxy is watching the others drift away, their light dimming, their messages taking longer to arrive. The universe isn't just expanding, it's growing apart. It's the grandest case of cosmic distancing imaginable. But how does this expansion actually work? The mathematical foundation lies in what physicists call the expanding metric, part of the general theory of relativity. In relativity, space-time isn't a rigid grid. It's a dynamic geometry that can stretch or curve depending on the matter and energy within it. The metric is the mathematical way of describing how distances are measured in that curved space-time. When we say the universe is expanding, what we really mean is that the metric, the very way distances are defined, is changing over time. This expanding metric is what gives rise to Hubble's law. Galaxies aren't accelerating away through space. The yardstick used to measure the distance between them is literally growing. The farther two galaxies are from each other, the more space there is between them to expand, so their apparent speed of separation increases. It's like drawing two dots on a rubber sheet. If you stretch the sheet slightly, the dots that were far apart move more than the ones that were close together, not because they're moving faster, but because the space between them grows more. Hubble's law also gave scientists a powerful new tool. By measuring how fast galaxies recede, we can estimate their distance, and by extension, the rate at which the universe is expanding. The value of that rate, the Hubble constant, has become one of the most important and hotly debated numbers in cosmology. Even today, nearly a century after Hubble's original work, astronomers are still refining it. Different methods of measuring it, whether using nearby stars, distant galaxies, or the faint afterglow of the Big Bang, give slightly different answers, leading to what's now called the Hubble tension. It's like two cosmic clocks disagreeing on what time it is, suggesting we may still be missing a piece of the puzzle. Hubble's discovery also had an unintended consequence. It gave us a way to estimate the age of the universe. If galaxies are moving apart now, and we can measure how fast, we can simply rewind the expansion to figure out when everything was closer together. That calculation points back to roughly 13.8 billion years ago, the moment when the universe began expanding from an incredibly hot, dense state. In a single leap, Hubble's law connected the present universe to its origin, bridging observation and cosmic history. What makes this all so remarkable is its universality. The same relationship holds whether you're looking at galaxies 10 million light-years away or 10 billion. The pattern doesn't depend on where you are or who's observing. Hubble's law is like the universe's signature move, a cosmic declaration that expansion is its defining behavior. And yet, it's a deeply personal one, too, because the farther away we look, the older the light we see. Each point on that line, each galaxy's redshift, corresponds not just to distance, but to time. The farther we gaze, the closer we get to the beginning. So, when you look at a distant galaxy through a telescope, you're not just seeing something far away. You're seeing it as it once was, billions of years ago, racing away from you faster than you can ever hope to follow. Hubble's law tells us that everything is receding, but it also tells us something more profound, that every observer, no matter where they stand in the cosmos, feels like they're at the center of expansion. The universe, it turns out, is the fairest system imaginable. No one's at the center, but everyone feels like they are. We're all floating in an infinite cosmic loaf that's still rising, watching our neighbors drift away and knowing we're drifting too. And while there may be no group therapy for that kind of separation, there's a strange comfort in knowing that every galaxy in the universe feels exactly the same way. There's a quiet kind of magic in the way light carries memory. Every photon that reaches our eyes or a telescope's mirror is a time capsule, an ancient messenger that left its home eons ago, traveling through the expanding universe to deliver a glimpse of what once was. When astronomers talk about redshift, they're not just measuring distance, they're unlocking time itself. A galaxy's redshift tells us how long its light has been on the road, and, by extension, how far back in cosmic history we're looking. You can think of the universe as a kind of museum of light, but instead of glass cases and velvet ropes, it uses time itself as the display barrier. The nearest stars show us the universe as it was a few years ago. Our own galaxy tells us a story millions of years old, and distant galaxies reveal scenes from billions of years ago. Epochs when stars were newborn, galaxies were colliding, and space was still buzzing with leftover radiation from the Big Bang. The farther out we look, the deeper we peer into the past. The cosmos doesn't just expand in space, it expands in time, and redshift is the key to navigating that timeline. Here's how it works. As light travels through the universe, space itself stretches, pulling on the light's wavelength and making it longer, redder, and older. The amount of that stretch, the redshift, tells us how much the universe has expanded since the light was emitted. A small redshift means the light hasn't traveled far or long. A high redshift means the light's been journeying for billions of years. Each degree of redshift corresponds to a specific moment in cosmic history. By measuring it, astronomers can reconstruct what the universe looked like at different ages, almost like scrolling backward through the universe's social media feed, except the posts are in starlight and the captions are written in wavelengths. When astronomers talk about a high redshift galaxy, they're referring to something staggeringly ancient. A galaxy with a redshift of 7, for example, is one we see as it was when the universe was less than 1 billion years old. A redshift of 10 or more takes us back to when the first stars and galaxies were just beginning to ignite. At that stage, the universe was a wild, chaotic place, dense, turbulent, and far hotter than today's calm, starry sky. Hydrogen clouds were collapsing into stars for the first time. Black holes were forming at galactic centers, and radiation filled every corner of existence. Our telescopes, in effect, are time machines. Machines that don't move us through time, but bring the past to us. The James Webb Space Telescope, for instance, was designed specifically to detect infrared light, the stretched, red-shifted glow of the earliest galaxies. When Webb peers into the deep sky, it's not looking at now, it's looking at what then looked like. It captures light that has traveled across space for more than 13 billion years, crossing a universe that's been expanding the whole way. When those photons finally hit Webb's detectors, they've been stretched beyond recognition, shifted from visible light into the infrared range. The telescope translates those ancient whispers of light into images of the young cosmos, revealing galaxies so distant they existed when the universe was just a few 100 million years old. It's hard to grasp what that really means. Imagine standing in a field at night and looking up at the stars. The light from the closest star system, Alpha Centauri, left just over 4 years ago. The light from the Andromeda Galaxy began its journey 2.5 million years ago, when early humans were still discovering fire. But the light from the most distant galaxies we can see? It started its journey when there were no stars like our Sun, no planets like Earth, and no creatures to wonder about any of it. Every glimmer is a story from a younger universe, and redshift is the translation of that story into numbers we can understand. This is why redshift isn't just a scientific measurement, it's a kind of cosmic archaeology. Instead of digging through layers of soil, astronomers dig through layers of time. Each redshift value corresponds to a different era, the epoch of Rauanization, when the first light broke through the fog of primordial gas. The era of galaxy formation, when massive structures began to assemble. The age of starlight, when stars fused the first heavy elements that would one day make planets, oceans, and people. Measuring redshift is like labeling the strata of the universe's history book. What's especially beautiful is that the universe records this history automatically. It doesn't hide its past. It broadcasts it endlessly across space. Every star, every quasar, every faint, red-shifted smudge in the telescope's field of view is a page from a different chapter of cosmic evolution. The only challenge is reading it before it fades. As the universe continues to expand, distant galaxies will eventually move so far away that their light will never reach us. The cosmic horizon, the limit of what we can see, is growing dimmer as galaxies slip beyond visibility. In a distant future, even the most powerful telescopes will see only the local neighborhood of galaxies. The rest of the universe's history will vanish from sight, hidden forever by the relentless stretching of space. But for now, we live in a privileged time. We can still look back and see the cosmos as it once was, an opportunity that future civilizations might not have. Every observation of a redshifted galaxy is a message from a bygone era, a postcard from the universe's youth. And these messages tell us not just where we came from, but what we're made of. The heavy elements in our bodies were forged in ancient stars that exploded long before our planet formed. The light from those stars traveled across expanding space, carrying the evidence of our own origins in its red-shifted glow. So when astronomers talk about redshift, they're really talking about memory. The universe remembering itself in the language of stretched light. Every photon that reaches us is a survivor of time, bearing witness to a cosmos that has changed and grown for billions of years. To measure redshift is to measure nostalgia, written in the faintest shades of red. And so, when we point our telescopes toward the dark and quiet sky, we're not gazing into emptiness. We're looking into a living archive of the past. The universe, it seems, is the best storyteller there is. It just tells its tales at the speed of light, stretched across time, painted in red. If you could somehow step into a time machine and visit the universe just a few 100,000 years after the Big Bang, you wouldn't see galaxies, stars, or planets. You'd be surrounded by a blinding fog of light, an endless, searing plasma of energy and particles so tightly packed that light couldn't travel freely. The cosmos back then wasn't the peaceful, star-speckled expanse we know today. It was more like a cosmic soup, dense, hot and glowing, with temperatures around 3,000 degrees. In that fiery haze, atoms couldn't exist. The moment electrons tried to settle around nuclei, high-energy photons would slam into them and tear them apart again. The universe was bright but opaque, a celestial sauna filled with light that couldn't escape. And then, after nearly 400,000 years of chaos, something extraordinary happened. The universe had expanded and cooled enough for hydrogen atoms to form and survive. When that happened, the fog lifted. For the first time, light could travel freely through space without being constantly scattered. The universe became transparent, and that first released light has been traveling ever since, cooling, stretching, and fading over billions of years. Today, that ancient radiation fills all of space, not as a blinding glare, but as a faint glow detectable in the microwave part of the spectrum. That glow is what we call the cosmic microwave background, or CMB. The CMB is not just old, it's the oldest light we can possibly see, a direct remnant from the dawn of the cosmos. It is the fossilized radiation of the moment the universe went from opaque to transparent, a kind of first light snapshot frozen in time. Every direction you look in the sky, that light is there, washing over the earth from all sides like a cosmic whisper. You can't see it with your eyes, but if your television ever displayed static on an old antenna, about 1% of that snow came from the CMB, the literal afterglow of the Big Bang, buzzing faintly through the fabric of existence. What makes the CMB so fascinating isn't just its age, it's what it tells us. Embedded in that ancient light is an incredibly detailed record of the universe's early conditions. When scientists map the CMB, they find it's astonishingly uniform, almost the same temperature everywhere, but not perfectly uniform. Tiny fluctuations, differences of just 1 part in 100,000, dot the map like freckles on a cosmic face. Those minuscule variations are the seeds of everything that exists today. Where the CMB was slightly denser, gravity would later pull matter together to form galaxies, stars, and planets. Where it was slightly less dense, vast cosmic voids would eventually open. In those faint ripples of ancient light, we can see the blueprint for the entire large-scale structure of the universe. The story of how we discovered this relic is almost accidental. In 1965, two radio engineers, Arno Penzias and Robert Wilson, were trying to eliminate a mysterious background noise in their radio antenna in New Jersey. They cleaned out bird droppings, adjusted equipment, and checked every connection. But the faint hiss remained, no matter where they pointed the antenna. Unbeknownst to them, across town, a group of physicists at Princeton University had been working on a theory predicting that leftover radiation from the Big Bang should still exist. When the two teams compared notes, they realized Penzias and Wilson's noise wasn't interference. It was the echo of creation itself. For that discovery, they won the Nobel Prize, and the universe suddenly had its baby photo. Over the decades, that photo has been refined. Satellites like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, revealing a speckled pattern that's both random and deeply meaningful. Those faint temperature differences, barely a few microkelvin, hold clues about the composition, shape, and destiny of the cosmos. From them, scientists have learned that the universe is roughly 75% dark energy, 20% dark matter, and just 5% ordinary matter, the stuff that makes stars, planets, and people. The CMB also confirms that space is flat on large scales, and that the universe's expansion began in a sudden, rapid burst known as inflation. In other words, this faint microwave glow is not just a remnant. It's the universe's autobiography written in radiation. What's truly mind-bending is how much this light has changed since it first escaped. When it was released, the universe was glowing with visible and infrared light, brilliant and searing, like the surface of a star. But as space expanded over 13.8 billion years, that light stretched, its wavelengths elongated, its energy drained, and its color reddened. The radiation that once glowed white-hot at 3,000 degrees Kelvin has cooled to a frigid 2.7 degrees above absolute zero. What began as fierce starlight has become a soft murmur of microwaves, stretched by the universe's relentless expansion. The CMB is, in a sense, the most dramatic redshift in cosmic history, a transformation from blinding brightness to near-invisible warmth. And yet, for something so faint, it's everywhere. Every cubic meter of space holds about 400 photons of CMB light, streaming in all directions. You are bathed in it right now, every second of your life. This light has been bouncing around the universe since before there were stars to shine it, before there were galaxies to hold it, before there was even a Milky Way to drift within it. When you detect the CMB, you are seeing the moment the universe took its first clear breath. There's a certain poetic irony to it all. The CMB, this ancient, nearly invisible radiation, isn't loud or violent anymore. It doesn't roar like the Big Bang once did. Instead, it hums quietly in microwaves, faint but persistent, like the fading echo of a song that began before there were ears to hear it. Every flicker of that background light is a reminder that the universe once burned brighter than any star, and that time and expansion have stretched that brilliance into a whisper. In a way, the CMB is the ultimate family portrait. It's not polished or posed, it's grainy, uneven, and glowing with potential. But within that glow lies the story of everything. The beginning of structure, the imprint of primordial sound waves, and the evidence that the universe was once young and full of fire. The next time you look up at the night sky and marvel at the darkness between stars, remember that it's not truly dark at all. Hidden in that blackness is the oldest light of all, still traveling, still whispering, still reminding us where it all began, the soft, stretched-out glow of the universe's first dawn. If the universe had a soundtrack, supernovae would be its symbol crashes, rare, dramatic, and impossible to ignore. They are among the most violent and luminous events in the cosmos, outshining entire galaxies for brief moments before fading into darkness. But to astronomers, these cosmic explosions are more than just spectacular light shows. They are precise measuring tools, ticking across cosmic time like luminous clock hands. By studying supernovae, scientists can trace how fast the universe expands, and even how that expansion has changed over billions of years. To understand how, let's start with what a supernova actually is. Most stars, like our Sun, end their lives quietly. They burn through their nuclear fuel, puff up, and shed their outer layers into space. But some stars, those that live fast and die young, go out with a bang. When a massive star collapses under its own gravity, its core implodes, sending a shock wave racing outward. The result is a titanic explosion that can release more energy in a few seconds than our Sun will produce in its entire lifetime. The light from these cataclysms travels across space, carrying valuable information about how far away the explosion occurred and, indirectly, how the universe itself has evolved. But not all supernovae are created equal. Some are chaotic and unpredictable, while others are remarkably consistent. Astronomers love consistency, especially when trying to measure vast distances. That's where type Ia supernovae come in, the universe's most reliable cosmic yardsticks. These particular explosions occur in binary star systems, where a white dwarf, a dense Earth-sized remnant of a dead star, steals matter from its companion. As it gorges on stolen gas, it grows heavier and hotter until it reaches a critical mass, about 1.4 times the mass of the Sun. At that exact threshold, physics throws in the towel. The white dwarf ignites in a runaway thermonuclear explosion, obliterating itself completely. Here's the beauty of it. Because all type Ia supernovae detonate at nearly the same mass, They all shine with roughly the same intrinsic brightness. It's as if the universe uses one standardized firework for these cosmic celebrations. That makes them ideal standard candles, objects whose true brightness is known, allowing scientists to calculate distance based on how dim they appear. The dimmer the explosion looks from Earth, the farther away it must be. Combine that distance with the supernova's redshift, how much its light has been stretched by the universe's expansion, and you've got a way to measure how fast the universe is expanding at that point in time. This is how astronomers effectively turn the universe into a timepiece. Every supernova they observe acts like a timestamp from a different era. By collecting data from many supernovae across different distances, they can chart how the rate of expansion has changed over billions of years. It's like watching a slow-motion video of the cosmos stretching frame by frame, with each bright flare marking another tick of the universal clock. This method, using supernovae to measure cosmic expansion, reached its most astonishing conclusion in the late 1990s. Two independent research teams, both observing distant Type Ia supernovae, expected to confirm that the universe's expansion was slowing down under the pull of gravity. After all, if you toss a ball upward, it eventually slows and falls back. Surely, the universe would behave the same way. But when they analyzed their data, they found the opposite. The most distant supernovae appeared dimmer than expected, not because they were farther away than thought, but because the universe had expanded faster than anyone imagined. Instead of slowing, cosmic expansion was speeding up. That discovery sent shock waves through physics. It implied that something mysterious was counteracting gravity on the largest scales. Some invisible force pushing galaxies apart faster and faster. Scientists dubbed this phenomenon dark energy, a name that is both descriptive and humbly vague. We don't know what it is, but we can measure what it does, and supernovae were the first messengers to reveal its presence. In one luminous stroke, these exploding stars reshaped our understanding of the cosmos. The precision of supernova measurements is astonishing. Astronomers analyze not just how bright a supernova appears, but how its light evolves over time. A Type Ia supernova brightens to its peak and then fades in a predictable pattern. By comparing these light curves across many events, researchers can fine-tune distance estimates and test models of cosmic expansion. The farther away the supernova, the older the light, and the deeper into the universe's past we're peering. Some of the most distant supernovae we've detected exploded when the universe was less than half its current age. You might think measuring something so faint and far away would be guesswork, but modern observatories have turned it into an art form. Telescopes like the Hubble Space Telescope and the upcoming Vera Rubin Observatory specialize in spotting these fleeting explosions across billions of light years. When one appears, teams of astronomers race to capture its light before it fades, dissecting its spectrum to determine its redshift and comparing its brightness to nearby standard explosions. Each observation adds another data point to the cosmic expansion graph, a record of how the universe's pace has evolved over time. Beyond measuring expansion, supernovae also serve as laboratories for the laws of physics. They allow scientists to test the consistency of natural constants across time and space. If Type Ia supernovae in the early universe behave differently than those nearby, it could mean the laws of nature themselves have evolved. So far, they seem reassuringly steady, But the fact that we can even ask such questions shows how powerful these cosmic beacons are. There's something deeply poetic about it all. Supernovae are the deaths of stars, yet they're the tools we use to measure the life story of the universe. They are both endings and beginnings, destroying themselves to illuminate the history of everything else. Each explosion is a farewell so bright it becomes a measurement of time itself. The next time you see a news headline about a distant supernova discovered by some far-seeing telescope, remember, that isn't just an explosion. It's a message from billions of years ago, written in starlight and delivered through an expanding cosmos. It tells us how the universe has stretched, how it has aged, and how it continues to evolve. Supernovae may burn out in weeks, but the stories they tell will echo for as long as there are eyes and telescopes to read them. For most of human history, the cosmos seemed like the ultimate symbol of stillness. The stars hung motionless in the sky, a backdrop for everything that moved on Earth. Even when we learned that galaxies were rushing away from each other, that the universe was expanding, it was easy to imagine that expansion as something slowing down over time. After all, that's what happens to everything else. If you throw a ball, it eventually stops. If you fire a rocket, it coasts and slows against gravity. Surely, the same must be true for the universe. That was the thinking of astronomers for decades, until the late 90s, when reality threw the biggest cosmic curveball imaginable. The story begins with two rival teams of scientists. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their goal was simple but profound: to measure how much the universe's expansion had slowed over time. Using type Ia supernovae, those reliable cosmic yardsticks that act as standard candles, the teams set out to map the universe's past and determine its fate. The assumption was that gravity, the great cosmic glue, would be tugging everything back together, gradually decelerating the expansion. Maybe, with enough matter, the universe would someday stop expanding altogether and begin collapsing back inward in a fiery big crunch. But when the data started rolling in, something was off. Something wonderfully, shockingly off. The distant supernovae didn't look as bright as they should have if the universe were merely slowing down. They looked too dim, as if they were farther away than expected. That could only mean one thing. The universe hadn't been coasting. It had been accelerating. Space itself was expanding faster and faster with time. The farther the scientists looked into the past, the more they saw evidence that the rate of expansion was slower back then. In other words, the universe was speeding up. This revelation was so bizarre that many astronomers initially thought it had to be a mistake. The idea that expansion could accelerate defied intuition. It was as if the universe had put its foot on the gas pedal billions of years after the Big Bang. For decades, cosmologists had been calculating models of how much gravity, driven by all the matter in the cosmos, should be slowing expansion down. Now, suddenly, there was something out there not just counteracting gravity, but overpowering it. That something got a name: dark energy. The name sounds like it was plucked from a science fiction script, but it's the best we've got for a phenomenon we barely understand. Dark energy is the mysterious force driving the acceleration of the universe's expansion. It doesn't behave like normal matter, which clumps together under gravity. It doesn't emit light, interact with forces in the usual way, or gather in galaxies. Instead, it seems to be woven into the very fabric of space itself, a property of the universe that pushes rather than pulls. Here's the strange part. The more space there is, the more dark energy there seems to exist. As the universe expands, it creates more room for dark energy, which in turn causes even faster expansion, a self-reinforcing loop of cosmic acceleration. Imagine blowing up a balloon that somehow manufactures its own air as it grows. The more it inflates, the faster it inflates. That's our universe right now, an ever-speeding balloon of existence, powered by something invisible and untouchable. To put the discovery into perspective, imagine the surprise of astronomers. For almost a century, the big cosmic debate had been between two futures: eternal expansion or eventual collapse. But the discovery of dark energy added a third option: eternal acceleration. Instead of slowing to a stop or reversing direction, the universe was doomed to speed up forever. Galaxies would drift farther and farther apart until, eventually, distant stars would disappear beyond the reach of our telescopes. The night sky, billions of years from now, would grow emptier, darker, and lonelier. The implications of this discovery were so monumental that it earned Perlmutter, Schmidt, and Ries the 2011 Nobel Prize in Physics. But their victory came with a catch. We still don't know what dark energy actually is. It makes up about 70% of the total energy in the universe, yet remains one of the greatest mysteries in all of science. We can measure its effects precisely. Its fingerprints are visible in the cosmic microwave background, in galaxy surveys, and in the distribution of large-scale structures, but its nature eludes us. One possibility is that dark energy is a property of empty space itself, a constant energy density that Einstein once included in his equations as the cosmological constant. He originally introduced it to keep the universe static, a move he later regretted, but it might turn out he was more right than wrong. If the vacuum of space naturally contains energy, that energy would push outward uniformly, driving acceleration. Another possibility is that dark energy isn't constant at all, but a dynamic field, something that changes over time, like a slowly shifting background current. Cosmologists call this idea quintessence, a poetic throwback to the ancient term for the mysterious fifth element beyond earth, air, fire, and water. Whatever its nature, dark energy has reshaped how we think about the cosmos. It means the universe's fate is sealed in a way that is both awe-inspiring and slightly tragic. If acceleration continues indefinitely, galaxies beyond our local group will drift so far away that their light will never reach us again. Future astronomers, living in the far future, may look up and see nothing beyond their own galaxy cluster, completely unaware of the vast universe that once surrounded them. The cosmos is literally pulling its own story apart, scattering the evidence of its origin faster than it can be observed. Yet there's something profoundly beautiful about this mystery. Dark energy reminds us that the universe is still full of surprises, that even after centuries of watching the skies, we've barely scratched the surface of what reality has to offer. It's the cosmic equivalent of finding out your quiet, dependable universe has been secretly training for a marathon and just sprinted out of view. The discovery of cosmic acceleration didn't just change cosmology, it humbled it. It reminded us that the cosmos doesn't owe us simplicity. The universe isn't winding down, it's revving up. And whether dark energy is a property of space, a dynamic field, or something stranger still, one thing is clear. The universe is not content to sit still. It's still expanding, still accelerating, and still keeping a few secrets hidden in the dark. If the story of the cosmos were a movie, we'd be living in the middle of the slow fade-out. The grand scenes are still visible. The brilliant galaxies, the sprawling nebulae, the ancient light that paints the sky. But the ending credits have already begun to roll. Each day, the universe grows a little emptier, a little dimmer, and a little older. The light from distant galaxies stretches further, losing energy as space itself expands. Over unimaginable stretches of time, that expansion will do more than just move galaxies apart. It will rewrite what time even means for those distant realms. Right now, when astronomers look deep into space, they're also looking deep into the past. The farther a galaxy is, the longer its light has been traveling to reach us. But because the universe is expanding, the light from those galaxies is often also being stretched. Its wavelength grows longer, its color reddens, and the information it carries becomes fainter. The faster the expansion, the greater the redshift. Eventually, as the universe continues to accelerate under the influence of dark energy, some galaxies will slip beyond what's called the cosmic event horizon, a kind of ultimate boundary beyond which their light will never reach us, no matter how long we wait. This isn't a metaphorical horizon. It's real, though invisible. Beyond that line, space is expanding faster than light can cross it. Any photon trying to make the journey toward us is trapped in a losing race. The finish line keeps moving away faster than the photon can travel, stretching the light into oblivion. From our vantage point, those galaxies don't just grow dim. They seem to slow down in time. Their flickers of light take longer to arrive. Their rhythms stretch out. Their activity appears to crawl. It's not because the galaxies themselves are changing speed, but because the expanding fabric of the universe distorts how their time flows relative to ours. In a sense, we are watching time itself unravel at the edges of the cosmos. Events in faraway galaxies appear to happen more and more slowly, until they seem to freeze entirely. A supernova that erupts in a distant galaxy might play out over seconds in its own frame, but to us it could stretch across years, centuries, or even longer. Eventually, as that galaxy recedes past the horizon, its light will redshift so dramatically that it will become undetectable. To future astronomers, it will be as if the galaxy never existed at all. That's the eerie consequence of eternal acceleration. The universe isn't merely growing, it's forgetting. Every second, more galaxies vanish beyond the cosmic horizon, taking their light, their histories, and their stories with them. The universe is slowly erasing its own record, not through violence or destruction, but through the gentle, relentless stretching of time and space. What remains visible will shrink until only our local group of galaxies, the Milky Way, Andromeda, and a few smaller companions, stay gravitationally bound together. Everything else will fade into darkness, receding faster than light, unreachable forever. In that far future, the night sky will look very different. To any beings that might exist then, the universe will appear static and empty. They'll see a few nearby galaxies merged into a single mega-galaxy, glowing quietly in a sea of blackness. The cosmic microwave background, the faint afterglow of the Big Bang, will have redshifted into wavelengths so long they'll be impossible to detect. The great cosmic clues that once revealed the universe's origin and expansion will be gone. Those future observers might believe they live in a small, eternal island universe, unaware that beyond their horizon lies the vast, forgotten sea of galaxies that once filled the cosmos. For us, standing at this particular moment in cosmic history, that future feels distant, but cosmically speaking, it's just around the corner. We live at a special time, the era when the universe is still transparent, still luminous, and still filled with ancient light. The photons that reach our telescopes today began their journeys billions of years ago, before our sun was born, before our planet even existed. We are the lucky generation that can still see the universe's childhood in the glow of distant galaxies. The window is wide open now, but it's slowly closing. The idea that time itself could freeze for distant galaxies might sound like science fiction, but it's simply a consequence of relativity and expansion. From our point of view, time in a galaxy moving away at nearly the speed of light slows dramatically. Push that expansion further, and the time dilation becomes infinite, meaning that galaxies' future, from our perspective, never arrives. It's not that time stops there, it's that the link between our times is severed. We'll never see their next moment. Their light fades, and their story ends, at least for us. If there's any comfort in this cosmic melancholy, it's that the process is beautifully predictable. The redshift of light encodes both distance and time, so we can actually watch the universe's memory loss in slow motion. Every spectral line, every dimmed galaxy, every stretched photon is a whisper of what's being left behind. The redshift tells us not only how far away something is, but how long ago it was. It's the universe's diary, written in fading ink. And perhaps that's the most poetic truth of all. The universe doesn't lose its memories all at once. It lets them drift away, one wavelength at a time. The galaxies that disappear beyond the horizon aren't gone in the physical sense. They continue existing, forming stars and living their cosmic lives. It's just that their story no longer reaches us. Like postcards from old friends, their light was sent long ago, and we're the last to receive it. Someday, countless eons from now, the universe will be vast, cold, and nearly silent. But in every dark patch of that future sky, hidden in the endless night, will still exist the echoes of what once was, a universe that burned, expanded, and stretched time itself to the breaking point. For now, we can still see those echoes. We can still measure them, still marvel at them. We're witnessing the last era when the cosmos is fully visible, before redshift turns the lights out. The universe, it seems, isn't just growing older, it's learning how to forget. Whenever a great discovery shakes science, there's always a period of cosmic debate. The expansion of the universe was no exception. When Edwin Hubble first announced that galaxies were receding, many scientists found the idea too wild to accept. An expanding universe implied a beginning, and that was uncomfortable for those who believed the cosmos must be eternal and unchanging. Naturally, alternative theories sprang up, attempts to explain redshift without rewriting the entire story of reality. One of the earliest and most persistent of these was the tired light hypothesis, proposed in the 1920s and 1930s. The name alone sounds like something the universe might say after a long day of existing. The idea was simple. Maybe light loses energy as it travels through space. If photons gradually tire out during their journey, they'd lose energy, and since energy determines wavelength, their color would shift toward red. Voila! Redshift, without any need for expanding space. It was an elegant idea on paper, the kind of theory that makes you pause and think, maybe. But science, as it tends to do, asked for receipts. If light really got tired, it would mean that photons scatters or interact with something during their cosmic voyage, losing just a little energy at each step. But this idea quickly ran into trouble. For one thing, if photons were bumping into something, dust, particles, hidden fields, they'd scatter. That scattering would blur distant galaxies, making them look fuzzy or smeared. Yet when we observe faraway galaxies, they're crisp and sharp. Their light may be redshifted, but their images aren't distorted. Whatever light is doing on its way here, it isn't slowing down because it's tired. It's stretching because space itself is doing the stretching. Another fatal blow came from supernova time dilation, a phenomenon we can actually observe. When astronomers watch distant supernovae, the explosions appear to unfold more slowly than identical ones nearby. Their light curves are stretched in time, just as redshift predicts for an expanding universe. If redshift were caused by tired light, only the wavelengths would change, not the timing of the event. The explosion would look just as fast, only redder. But in reality, distant supernovae both redden and slow down in perfect harmony with the predictions of a cosmic expansion. The tired light theory collapses under its own laziness. Then there's gravitational redshift, another contender that sounds plausible until you dig into the details. Einstein's general theory of relativity tells us that light can lose energy when it climbs out of a gravitational field. For example, photons escaping from a star or black hole get stretched as they climb against gravity's pull, shifting toward red. This is a very real effect. We've measured it in laboratories and observed it in the light from dense stars. So, could this explain the redshift of distant galaxies? Not quite. Gravitational redshift works locally, in regions where there's a strong gravitational field. But galaxies aren't sitting in one giant cosmic pit. The redshift we see across the sky increases smoothly with distance, not in patterns tied to mass or gravitational potential. If gravitational redshift were responsible, we'd expect light from galaxies near massive clusters to be significantly more redshifted than light from empty regions of space. That's not what we see. The redshift pattern is beautifully uniform, every direction, every distance, exactly as you'd expect if space itself were expanding evenly everywhere. Over time, these alternative theories fell away one by one, leaving the expanding universe standing tall. But the debates weren't in vain. They forced astronomers to refine their data, build better instruments, and test their assumptions to the breaking point. And as each new line of evidence arrived, the cosmic microwave background, the large-scale structure of galaxies, the accelerating expansion, every piece fit perfectly into the puzzle of a growing universe. Still, the tired light idea never completely died. Like a cosmic zombie, it keeps reappearing in pop science forums and conspiracy corners, often dressed up with modern buzzwords. The argument usually goes something like, maybe light just loses energy to quantum effects or dark matter. But whenever these ideas are tested against the vast troves of observational data, from supernovae to galaxy clusters to cosmic background radiation, they crumble. The universe's redshift pattern doesn't match a tired traveler. It matches a dynamic stage that's constantly stretching beneath everything on it. There's also a subtle elegance in how expansion explains more than just redshift. It explains why distant galaxies look younger, because we're literally seeing them in the past. It explains why the cosmic microwave background exists, because light from the early universe was stretched into microwaves by billions of years of expansion. It explains why the large-scale structure of the universe has grown from small ripples in the CMB into sprawling webs of galaxies. Alternative theories can imitate one or two of these facts, but not all of them. Expansion ties them together seamlessly, like threads in a cosmic tapestry. To be fair, skepticism has always been science's best friend. Every great idea needs to be poked, prodded, and tested before it earns its crown. The expanding universe wasn't accepted because it sounded poetic. It was accepted because it predicted everything from galaxy motion to the afterglow of the Big Bang with uncanny precision. Einstein's equations describe it. Telescopes confirm it. And every new discovery, from distant quasars to gravitational waves, falls neatly into place. If anything, the story of Redshift and its challengers is a reminder of how science works at its best. Ideas compete, data decides, and reality gets the final word. The universe doesn't care what sounds tidy or intuitive. It behaves the way it does, and it leaves clues in the light for us to follow. So, the next time someone tells you the universe is just tired, you can smile and say, no, it's ambitious. The cosmos isn't slowing down on its journey. It's expanding, accelerating, and evolving in ways that no alternative theory has ever fully captured. The light from distant galaxies isn't fading from exhaustion. It's being stretched across an ever-growing stage. Space, it seems, has big dreams, and it's not done chasing them yet. It's one of the most delicious cosmic ironies. The deeper we look into the universe, the slower everything seems to move. Explosions that last seconds in distant galaxies appear to unfold in slow motion, and the ticking of cosmic clocks far across space drifts out of sync with our own. From our vantage point, time itself seems to yawn and stretch the farther it reaches. Yet, here at home, everything feels normal. The seconds still march stubbornly forward, your phone alarm still rings at the same annoying pitch, and entropy still makes sure your toast lands butter side down. So, what's really going on? Is time truly slowing down? Or is the universe just playing a magnificent optical illusion? To answer that, we have to accept something Einstein figured out over a century ago. Time is not a universal metronome ticking the same everywhere. It's flexible, relative, and deeply intertwined with space. Together they form a single fabric, space-time, that can stretch, warp, and twist depending on what's happening in the universe. When we talk about time slowing down for distant galaxies, we're not saying their clocks are faulty or lazy. We're saying the fabric they live on has been stretched differently than ours. Think of space-time as a cosmic sheet of elastic. When that sheet expands, it doesn't just pull galaxies apart, it also stretches the intervals between moments. Light that travels across that stretched sheet carries the evidence of that distortion in its wavelength. Its crests and troughs arrive farther apart, and the rhythm of the light, the timing of its oscillations, slows. So, when we observe distant galaxies, we're not only seeing stretched light, we're seeing stretched time. Every blink, every flare, every pulse from a distant source drags, like a film played in slow motion. Locally, of course, time feels perfectly fine. That's the strange part. Within your own frame of reference, time always feels steady. The laws of physics don't change from one second to the next. Your heartbeat doesn't suddenly slow because the universe is expanding. Relativity ensures that every observer experiences time as normal in their own bubble of space-time. The weirdness only emerges when you compare two different regions, like us, here in the Milky Way, and a galaxy 10 billion light-years away. From our point of view, that distant galaxy's processes unfold more slowly. From its own point of view, everything is perfectly ordinary. The discrepancy isn't in the galaxies, it's in the geometry connecting them. This cosmic stretching of time gives us a profound window into the universe's history. When astronomers measure redshift, they're not just measuring color. They're measuring how much the universe's clock has changed since that light was emitted. A galaxy whose light has doubled in wavelength has also had its clock stretched by the same factor. That means we're literally watching the pace of time change with distance. Time itself becomes a kind of map, a gradient across the expanding cosmos. The deeper implication is both humbling and poetic. There's no single now that applies everywhere. The universe doesn't share a universal present moment. The word now only makes sense locally. When we look at a galaxy a billion light-years away, we're seeing it as it was a billion years ago, and the passage of its time since then has diverged from ours. Our cosmic conversation with that galaxy is delayed and distorted by the expansion of the universe. If the cosmos were an orchestra, every section would be playing at its own tempo, all connected by the stretching of space-time. From this perspective, the redshift isn't just about motion or color. It's a reminder that time is relative in the grandest sense. It's evidence that the universe doesn't run on one clock, but on countless clocks, each ticking to its own rhythm depending on where and when it resides. This realization reshapes how we think about the past and future. There's no objective line dividing them across the cosmos, only light traveling, carrying fragments of then into our now. This isn't just philosophy. It has practical consequences for how we interpret the cosmos. When astronomers study distant galaxies or supernovae, they have to correct for time dilation. A distant supernova that takes 2 weeks to fade nearby might appear to take a month when viewed from Earth because its entire timeline has been stretched by expansion. Understanding that relationship allows scientists to use these time distortions as cosmic rulers, measuring how much space has expanded since the light began its journey. In other words, by watching time slow down elsewhere, we can measure how much time has passed for the universe itself. It's strange to realize that our place in the cosmic story is both special and temporary. We live in a fleeting era when the universe is still transparent enough for us to see its past, when Redshift still links us to galaxies billions of light years away. But as cosmic acceleration continues, those galaxies will slip beyond view, their light stretched until it fades completely. In the far future, no one will be able to measure this cosmic time stretch. The story will still be happening, but its pages will no longer reach us. From our cosmic balcony, then, we occupy a remarkable vantage point. We can look back and see time unfolding in different tempos across billions of years. The red-shifted light that streams into our telescopes is not just a relic, it's a performance. Time itself dancing across an expanding stage. Every wavelength is a beat in the cosmic rhythm, every photon a fragment of the universe's unfolding song. So, is time really slowing down? The answer depends entirely on where you stand. For us, time feels normal. For distant galaxies, it seems to drag. But the truth is subtler. Time doesn't slow. It stretches. It's a fabric being pulled gently apart, expanding the intervals between moments just as it expands the distances between galaxies. And perhaps that's the ultimate cosmic lesson. The universe is not a static picture, but a living, breathing continuum of time and space. What we call the present is just one thread in that fabric, connected to countless others across an unfathomable expanse. The redshift is the universe's quiet way of reminding us that we're part of something far grander, something where even time itself bends to the rhythm of creation. In the end, when we look into the night sky, we're not just looking outward, we're looking backward through time. Every faint glimmer, every stretched wavelength every photon that lands in our telescopes tells the same story. Time is not fixed, and the universe is not finished. We're watching the grandest clock ever built, ticking in slow motion, one cosmic heartbeat at a time.